Hello all, this is Sandeep Kumar and I welcome you back to my YouTube channel Math with Sandeep. We are in the chapter of continuity and already we have completed two videos in this particular chapter. In the first video we discussed about continuity of a function at a given point, and in second video we have discussed problems based on it. So in this particular video let us discuss about discontinuity of a function at a given point. When can I say that a function is discontinuous at a given point, and when can I say that it is continuous? We discussed already when can I say that it is continuous. So based on it, let us discuss about discontinuity and its types. Okay now, so in case if you are new to the channel, don't forget to subscribe the channel. Let us start the video. Let us discuss about the types of discontinuities. Basically there are two types of discontinuities, as you can see in the figure. It is either removable discontinuity or non-removable discontinuity. When can I say that it is removable discontinuity? Let us see first. Okay, if limit of the function exists but it is not equal to the value of the function, or if the value of the function is not defined. Okay, now keep this in mind. In this case, limit of the function exists, remember this, in removable discontinuity. And in non-removable discontinuity, limit of the function does not exist. Okay, now in removable discontinuity, again there are two types. One is missing point discontinuity and another is isolated point discontinuity. Similarly, in non-removable discontinuity, we have three types of discontinuity. One is finite type, another is infinite type, and the third one is oscillatory type. So let us discuss each discontinuity with proper example. Okay, let us start. Actually, a function is continuous at a given point x is equal to a if the left hand limit at x is equal to a is same as the right hand limit at x is equal to a, and which is also same as the value of the function f of a. Okay now, so if this condition is satisfied, then we can say that the function is continuous at x is equal to a, and we have learned this already. And if this condition is not satisfied, then we say that the function has discontinuity at x is equal to a. Okay now in how many different ways this condition will not be satisfied, let us discuss, and each type will become one type of discontinuity. Okay now, so case 1, these two will be equal. Okay, f of a minus will be equal to f of a plus, which means the limit exists, but this may not be equal to f of a, where f of a is a finite value, or f of a will not be defined. Okay now, so that is one type of discontinuity. And similarly, if limit itself does not exist, then it is another type of discontinuity. Now let us clearly discuss what are those types of discontinuities. First we will start with removable discontinuity. Dear students, in removable discontinuity, the limit of the function exists. What is it? Limit x approaches a, f of x exists. So which means what? The left hand limit is equal to right hand limit. Okay now, left hand limit will be equal to right hand limit, but the problem is that this limit will not be equal to f of a in one case, or f of a itself is not defined. So there are two possibilities in removable discontinuity. We will discuss about those two possibilities separately, but what you should remember means, in removable discontinuity, limit of the function exists, but it is either not equal to f of a, or f of a itself will not be defined. These two will be equal, but f of a will not be defined. Okay now, so remember this, in removable discontinuity, limit of the function exists. Okay now, but either this will happen or this will happen. Okay now let us clearly discuss what are the two types of removable discontinuity. The first one is missing point discontinuity. See, the first one in removable discontinuity is missing point discontinuity. What is missing point discontinuity means? Here obviously the left hand limit x approaches a minus f of x will be equal to limit x approaches a plus f of x. Okay, so which means the left hand limit will be equal to right hand limit. So the limit exists, but f of a is not defined. But f of a is not defined. Therefore, we say that f of x has discontinuity. F of x has discontinuity at which point? At x is equal to a. Okay, now the limit exists, but f of a will not be defined. For that reason, we say that the function has discontinuity at x is equal to a. To understand this missing point discontinuity, let us take an example. Here is an example. Let f of x is x square minus 5x plus 6 divided by x minus 3, and remember where x is not equal to 3. Okay, now since x is not equal to 3, let us simplify this given function. Okay, now let us see how to draw the graph of this particular function and its behavior around x is equal to 3. Okay, if you simplify the same function and if you factorize the numerator, you will get x minus 2 into x minus 3, and the denominator is x minus 3. Okay, where x is not equal to 3. Since x is not equal to 3, I can cancel x minus 3 and x minus 3, and the function becomes x minus 2. So f of x is nothing but x minus 2, where x is not equal to 3. Where x is not equal to 3. Okay, now let me find the limiting value of this function. Since it is a polynomial, we can directly find the limiting value of the function instead of taking LHL and RHL. So limit x approaches 3. I am talking about the limiting value of the function when x is approaching 3. Okay, f of x is equal to. So limit x approaches 3. Since x is only approaching 3, x is not exactly 3. Correct or not? X is not exactly equal to 3. So we can write f of x as x minus 2. And if you substitute x value as 3, you will get 3 minus 2, which is equal to 1. So the limiting value of the function, dear students, is equal to 1. But what about value of the function? I am talking about f of 3. But we cannot find what is f of 3 because the function is defined except at x is equal to 3. We cannot use the function when x is equal to 3. So f of 3 in this case is not defined. So for this reason, dear students, limiting value of the function exists, but the value of the function is not defined. For this reason, this function f of x has discontinuity. F of x has discontinuity at x is equal to 3. And what type of discontinuity is it? Since limiting value of the function exists and value of the function is not defined, we call it as what point discontinuity? This is called missing point discontinuity. So f of x has discontinuity at x is equal to 3, and what type? Which is missing point discontinuity. Missing point discontinuity. To understand why this particular name is given, let us understand the discontinuity of this function f of x using its own graph. Okay, I'm going to draw the graph of f of x which is equal to x minus 2. Okay, this and this both are same only in this given. If you draw the graph of this function, let us see what happens. Let us draw the graph of f of x is equal to x minus 3 where x is not equal to 3. Okay, now already you have learned how to draw the graphs in 7th, 8th, 9th, 10th itself. Okay, fine. Now when x is 0, if you substitute, you will get 0 minus 2 which is minus 2. So when x is 0, y is minus 2. Okay, now when x is 1, f of 1, what is f of 1? 1 minus 2 which is minus 1. So when input is 1, the output is minus 1. Okay, now let me take f of 1.9. When input is 1.9, the output is how much, dear students? 1.9 minus 2 which is minus 0.1. Okay, now 1 point minus 2 which is minus 0.1. Or let me take 2 itself, no problem. I'll take 2, f of 2. When input is 2, output is 2 minus 2 which is 0. So when input is 2, the output is 0. Here is the graph point. Okay, now next when input is 2.9, what happens when input is 2.9? 2.9 minus 2 is 0.9, correct? That means what? Any input is very close to 3. That means 2.9. The output is very close to 1, which is 0.9. 0.9 somewhere here. Okay. See, let me join the graph. It goes straight. Okay, now. But exactly when input is 3, we cannot use this function. So there is no value of the function. It's an open hole. Open hole means that at this input we do not have any output. Keep this in mind. Next, when input is 3.1, f of 3.1, comfortably we can substitute the value. F of 3.1 is 3.1 minus 2 which is 1.1, correct or not? 1.1. So when input is 3.1, the output is 1.1, just above it. When input is 4, f of 4 is equal to 4 minus 2 which is equal to 2. When input is 4, the output is 2. and for all other inputs we can use the function. Okay na? So what do we get here, students? Here we'll get a straight line. The graph is a straight line. Okay na? This is the graph of f of x is equal to x minus 2, where x is not equal to 3. Okay na? This is the graph of it. Observe one thing, the graph is continuous. You can continuously draw the graph of f of x is equal to x minus 2, but when input is becoming 3, I cannot continuously draw now. I have to remove my hand and then I should continue from here. So there is a discontinuity at what input? At input 3. And when input is 3, the value of the function is missing. The value of the function is missing. That is the reason why it is called what point? Missing point discontinuity. So when input is 3, there is no value of the function. Okay na? And remember one thing. The name is removable discontinuity. Why this particular name removable is given means you can redefine the function and you can make it continuous. Is it so? How to redefine a function? Now let us see. I'll write f of x is equal to, as usual, x square minus 5x plus 6 divided by x minus 3, and x is not equal to 3. Dear students, if you want this function to be continuous, when input is 3, what should be the output? The output should be how much? If I want to use this function, when input is 3, the output should be 3 minus 2. 3 minus 2 means 1, correct or not? So I will redefine f of x in such a way that when input x is equal to 3, the output is 1. I will redefine the function in such a way that when input is 3, the output is 1. Then what happens? When input is 3, the output is 1, this open hole gets closed. Now the function, I can draw the function continuously without lifting my hand. The function is now continuous. The function is now continuous at x is equal to 3. Correct or not? So I can redefine the function and I can remove the discontinuity. For that reason, these discontinuities are called removable discontinuity. Okay now, see, in missing point discontinuity, which is removable discontinuity, I can redefine the function to remove the discontinuity. Similarly, let us see what is next discontinuity. Now let us discuss about isolated point discontinuity. Okay, in this type of discontinuity, this is also removable discontinuity only. Even here also the limit of the function exists, which means that the left hand limit is equal to right hand limit. Okay now, and f of a also is a finite value. F of a is also a finite value, but the problem is that these two will not be equal to f of a. That means the limiting, what is it? So we can say that limit x approaches a, f of x exists. But this will not be equal to value of the function. Okay now, so let us take an example to understand isolated point discontinuity, and at the same time we will also see its graph. One of the best examples to discuss about isolated point discontinuity is f of x is equal to modulus of signum of x. Dear students, do you remember what is signum of x function? So signum of x is equal to plus 1 when if input is positive, and it is minus 1 if input is negative, and signum of x is equal to 0 if input is 0. So there are only 3 possible outputs for signum function. Either the output will be plus 1 or minus 1, or it will be 0. But we are talking about modulus of signum of x, correct or not? In that case, what is modulus of signum of x? When input is negative or when input is positive, it doesn't matter. The output will be plus 1. Because of modulus, modulus of plus 1 is 1, modulus of minus 1 is also 1, correct or not? So when input is not 0, the output is 1. For positive inputs also the output is 1, and for negative inputs also the output is 1 because of modulus. And when input is 0, the output is 0. So this is the the values of signum of x, modulus of signum of x. Now if you try to find the limiting value of this function f of x, no need to find LHL and RHL separately. When input is not 0, the output is always 1, no need to. Okay na? See, limit x approaches 0 f of x. I am trying to check the limit at x is equal to 0. Okay now, observe this. We are discussing about continuity of the function at x is equal to 0. Okay, in this case. Okay, so at x is equal to 0, the limiting value of the function, dear students. x is only approaching 0. So x is not equal to 0. Okay, now x is not 0, x is only approaching 0. So that means x is not 0 only, right? When input is not 0, f of x is equal to 1. So f of x is equal to 1. The limiting value of the function is what, dear students? 1. But what about value of the function f of 0? At x is equal to 0, what is the value of the function? When input is 0, the output is 0. So limiting value of the function is 1 and the value of the function is 0. So it means what? The limiting value of the function is not equal to value of the function. For this reason, we call the discontinuity at x is equal to 0 as what? Isolated point discontinuity. So what is the conclusion? Therefore, f of x has isolated point discontinuity. Isolated point discontinuity at x is equal to 0. There are only two types of discontinuity in removable discontinuities. One is missing point and another is isolated point. Okay, now, but let me draw the graph of it to have more clarity, and we will see why it is called isolated point discontinuity. If you draw the graph of this function, you will get clarity. So I will show you the graph also. Dear students, when input is 0, the output is 0, correct or not? Here is our graph point. But what happens if input is just more than 0? So then, even if it is 0.00001, okay, now it is a positive input. Okay, now when input is not, okay, when input is not 0, the output is 1, correct or not? So the output will be 1. When input is 1, when input is 1, the input is not 0, so the output is 1. When input is 2, the output is 1. When input is 3, the output is 1. Except at 0, for all other inputs, except at 0, for all other inputs, the output is how much? 1. So if I connect all these points like this, so and I have to keep here an open hole. I'll tell you what is the meaning of it. Dear students, when input is 0, this closed hole says that when input is 0, the output is 0 and not equal to 1. Open hole says that the output is not equal to 1 when input is 0. Okay, now please observe this. If I want to draw the graph now, I'll draw like this continuously. But exactly when input is 0, I have to remove my hand and I should go here. And then again I have to go here and I should go like this. So which means I cannot draw the graph continuously. So therefore, this particular function has a discontinuity at x is equal to 0. And please observe one thing. Here only this output point is isolated. Isolated means separated from here, correct or not? So only this particular point is separated from here, isolated. That's why this discontinuity is called what? Isolated point discontinuity. I hope it's clear. Okay, now so in this case, the left hand limit is approaching 1, the right hand limit is approaching 1, but the value of the function is not 1, it is 0. Okay, so this type of discontinuity is called isolated point discontinuity, and we can and this is why this discontinuity is also called as removable. Means here also we can redefine the function to make it continuous. Then how can I redefine the function to make it continuous? Redefining the function. How will I redefine the function to make it continuous? See, when input is not 0, I'll write here instead of writing like this. Okay, I'm redefining the function. F of x is equal to modulus of signum of x if input is not equal to 0. Which value you want? If you want to make it, if you want to draw it continuously, when input is 0, what output you want? You want 1 as output, correct or not? So when input is 0, you want 1 as output, so redefine the function. So what is it? F of x will be this function if x is not 0, and it will be 1 if x is 0. So if I redefine the function like this, then what happens? The output when input is 0 is not 0. The output is actually 1. Now if I draw the function, I can continuously draw it without lifting the hand. It becomes continuous. Okay, now so there will be questions where they will ask us to redefine the function to make it continuous. Obviously, if it is a removable discontinuity, we can redefine the function just like this. Obviously, we will see some problems, okay, now based on how to redefine the function. You'll get more clarity when we discuss the problems on it. So I hope you understood these two types of discontinuity. one is missing point and another is isolated point discontinuity. Next, let us discuss about non-removable discontinuities. Okay, first of all, let us see what is non-removable discontinuity, and after that we will start discussing about its types. Dear students, in non-removable discontinuity, okay, now let me erase this. In non-removable discontinuity, the limit of the function itself does not exist at x is equal to a. Limit x approaches a, f of x does not exist. So for this reason, okay, now that particular discontinuity at x is equal to a is called non-removable discontinuity. So whenever limit x approaches a, f of x does not exist, obviously for various reasons, we say that the discontinuity, what is it? We say that f of x is discontinuous at x is equal to a. And what type of discontinuity it is? It is non-removable discontinuity. Okay, there are three types of non-removable discontinuities. Let us see the first one, which is finite type discontinuity. Finite type. So, in finite type discontinuity, left hand limit is a finite number. Okay, even right hand limit is also a finite number. But left hand limit is not equal to right hand limit. Okay, now for this reason we say that limit x approaches a, f of x does not exist. And since the limit does not exist, the function is not continuous. Okay, now so once again, in finite type discontinuity, left hand limit is a finite number and right hand limit is a finite number, but left hand limit will not be equal to right hand limit, therefore the limit does not exist. And we will say that f of x is discontinuous at x equal to a. Okay, now so let us take an example to understand finite type discontinuity, which is also called as jump type discontinuity. So finite type discontinuity, it is also called as what? Jump type discontinuity. Okay, fine. Let us see an example to understand this. Here is a simple example, dear students. Okay, f of x is defined as x square minus 1 if x is less than 0, and f of x is x plus 1 if x is greater than or equal to 0. So in this case, let us discuss whether the function f of x is continuous at x is equal to 0 or not. So we are discussing about the continuity of the function at x is equal to 0. For this, let me find left hand limit first. So limit x approaches 0 minus f of x. So which means limit x approaches 0 minus. X is approaching 0 minus means x is just less than 0, correct? X is less than 0. So for f of x, we will take x square minus 1. We will take x square minus 1, and after that you can substitute x as 0. You will get 0 square minus 1, which is equal to 0. The left hand limit is 0. Now let us also discuss about right hand limit. Limit x approaches 0 plus f of x, which means limit x approaches 0 plus. Dear students, a small correction, 0 square minus 1 is minus 1. Okay, now come back to this. So limit x approaches 0 plus, f of x is x plus 1. Why f of x is x plus 1? Because x is approaching 0 plus, which means x is greater than 0. X is greater than 0, we should take f of x as x plus 1. Now we can substitute x value as 0. So 0 plus 1 is equal to 1. What did you observe? The left hand limit is minus 1 and the right hand limit is plus 1. Both are finite values, but they are not equal to each other. So in this case, left hand limit is not equal to right hand limit. Therefore, limit x approaches 0, f of x does not exist. So limit x approaches 0, f of x does not exist. So what do we say? Therefore, the function f of x has finite type discontinuity at x is equal to 0. So conclusion is f of x has finite type discontinuity. I'm just writing it in short form. Okay, now you can understand it. F of x has finite type discontinuity at x is equal to 0. So the function is discontinuous at x is equal to 0. But to understand this, okay, now even better, let me draw the graph of it. Okay. So let us see how to draw the graph of f of x is equal to the same function only. Okay, now when input is first greater than or equal to 0, let me draw this graph. When input is equal to 0, the output is 0 plus 1. When input is equal to 0, the output is 0 plus 1, which means 1. So this is the graph point. When input is 1, again the input is more than 0 only. Na? For all the inputs greater than 0, let me take f of x as x plus 1. When input is 1, 1 plus 1 is 2. When input is 2, 2 plus 1 is 3, and it goes like this. It is a straight line. Okay, now, but when input is just less than 0, even if it is minus 0.000000 and so on, then the function will be taken as x square minus 1, correct or not? So which means, what if x is equal to 0 here also? Then I'll get 0 square minus 1 and I'll get minus 1 here, correct or not? But x is not equal to 0. So which means the graph starts from here, but with an open hole. The graph starts from here. Okay, now, and obviously it is a parabola, as you have known already. So the graph point is here and it will go like this. When input is minus 1, when input is minus 1, it is less than 0. So minus 1 whole square minus 1 will be 0. The graph goes like this. It's a parabola. When input is minus 2 whole square is 4, minus 1 is 4 minus 1, which is 3. When input is minus 2, the output is 3. So obviously it is a parabola. You should have known already. Correct or not? Observe one thing, dear students. If I want to draw the graph, I will come like this. But you cannot draw the graph continuously. You have to lift your hand, you have to jump to this output, and you should go like this. So while drawing the graph, I came up to here and I am jumping to this point and I am going like this. Correct? For this reason, this finite type discontinuity is also called as what? Jump type discontinuity. Okay, now, and sometimes they will ask us to find the jump value. What is the jump value? They will ask. Jump value means very simple, dear students. It's the modulus of difference between these two outputs. Modulus of difference between these two outputs. This output is 1 and this output is minus 1. So larger value minus smaller value. Larger value minus smaller value. So what will you get? 1 plus 1, you will get 2. So the value of this jump is how much, dear students? 2. So it is jumping 2 units and then again it is going like this. In problems they will also ask us to find this jump value. Remember this. So finite type discontinuity is also called as jump type discontinuities. And one of the best examples of the functions which have jump type discontinuity is the greatest integer function. Okay, I'll just give you a simple idea about that greatest integer function and we will go with the next type. This is the step function, greatest integer function, f of x and its graph. Obviously, if you see, I cannot draw the graph continuously. I have to lift my hand, I have to jump here and again I can draw like this. Again I have to jump here and again I have to draw like this. Jump here and draw like this. So it's very much obvious that here the function has discontinuities at what inputs. The function is discontinuous at what inputs? At all integers. At all integers. At 1, x is equal to 1, at x is equal to 2, at x is equal to 3, at x is equal to 0, at x is equal to minus 1. The function is discontinuous. And what type of discontinuity is it? You are jumping to this point, you are drawing like this, you are jumping to this point. It is jump type discontinuity, which is nothing but finite type discontinuity. And what is the value of the jump, dear students? So this output minus this output. So 1 minus 0. So the jump value here is larger output minus smaller output, which is 1 minus 0, which is 1. Everywhere the jump value is 1 unit. Okay, now, so this is one of the best examples for the finite type discontinuities. And let us go for the next type, which is infinite type discontinuity. The second type of non-removable discontinuity is infinite type discontinuity. So what does it means? Here also limit of the function does not exist, but the thing is either the left hand limit or the right hand limit or sometimes both. They approach plus or minus infinity. What is the meaning of it? So in some examples, only left hand limit will be taking plus or minus infinity, plus infinity or minus infinity. And in some examples, only right hand limit will be taking plus infinity or minus infinity. And in some examples, both LHL and RHL will be approaching infinities. So in that case, we call them as infinite type discontinuities. And one of the best example for infinite type discontinuity is f of x is equal to 1 by x, and remember x is not equal to 0. Correct, dear students? See, at x is equal to 0, you try to find out left hand limit and right hand limit at x is equal to 0. Let us find left hand limit. Okay, now, so left hand limit means what? Limit x approaches 0 minus 1 by x. Already in limits chapter we have discussed. X is approaching 0 minus. What is the meaning of it? It is 1 divided by minus 0.00000 and so on. X approaches 0 minus means minus 0.0000 and so on. This is what? Minus infinity. I am not saying that the value is exactly minus infinity. So this value is approaching minus infinity. Similarly, dear students, what is right hand limit? Limit x approaches 0 plus 1 by x. 0 plus means 1 divided by 0.0000 and so on. And its value is approaching plus infinity. See, observe, in this case, left hand limit is also taking minus infinity and right hand limit is also taking plus infinity. Correct or not? Obviously, limit does not exist. Okay, and this type of discontinuity is called what discontinuity? Infinite type discontinuity. Here limit does not exist. Limit LHL is not equal to RHL. So for that reason we will say that it is infinite type discontinuity. Okay, now, and you can also check its graph once. Already we have drawn this graph many a times in the previous cases. Okay, so the graph of f of x is equal to 1 by x will be taken like this. You can try to plot it using different inputs. Okay, so this is the graph of f of x is equal to 1 by x. So as x is approaching 0 from the left side, the output is taking minus infinity, and as x is approaching 0 from the right side, the output is taking plus infinity. Okay, now, so obviously left hand limit is not equal to right hand limit, and we say that it is infinite type discontinuity. And I have given a different name, asymptotic type. What is the meaning of it? It is also called as asymptotic type discontinuity. And what is it means? At x is equal to 0, if you observe, this line is there now, which is y-axis. Y-axis is looking like a tangent to this curve. Looking like a tangent, it is not exactly a tangent. So there is a vertical tangent at x is equal to 0. Okay, now, so when it will touch the curve, if the output reaches plus infinity, or if the output reaches minus infinity, then this line, this vertical line will touch both the curves. But we all know that we cannot reach plus infinity or minus infinity. Correct or not? Here the vertical line y is equal to 0, which x is equal to 0, which is y-axis, looks like it is a tangent to the curve. Correct or not? So this kind of lines, this kind of vertical tangents, they are called as asymptotes. We will discuss more about asymptotes in upcoming chapters of applications of derivatives. For now, okay, anyhow, here y-axis is asymptote for this particular curve, so that's why we call it as asymptotic type discontinuity. And remember one thing, it is not necessary that both should be approaching plus infinity or minus infinity. It is only left hand limit can approach plus infinity and right hand limit can be a finite value, or right hand limit can approach plus infinity and left hand limit can approach a finite value. I'll give you a simple example on it. Here is this function f of x is equal to e power 1 by x. Okay, now let us try to find the left hand limit and right hand limit at x is equal to 0. Okay, at x is equal to 0, what is left hand limit, dear students? X approaches 0 minus f of x. And we all know that when x is approaching 0 minus, just now we discussed that 1 by x is approaching minus infinity. Correct or not? So then the question becomes what? Limit x approaches 0 minus, okay, e power 1 by x is taking what value? Minus infinity. So no need of limit, we can directly substitute 1 by x as minus infinity. And already in the chapter of limits we discussed that improper fraction, e is approximately 2.71. Improper fraction, 2.71 is improper fraction. Power minus infinity, improper fraction power minus infinity is 0. We have discussed it in limits chapter, do check it once. Okay, now, so the left hand limit is equal to 0. What about right hand limit? Limit x approaches 0 plus f of x. So which means e power, what is it? We can write directly e power, as x is approaching 0 plus 1 by x is approaching plus infinity. So it is e power infinity, which is equal to infinity. Improper fraction power infinity is infinity only. So in this example, only right hand limit is approaching infinity. Left hand limit is not approaching infinity. Left hand limit LHL, this LHL is a finite value, but of course 0 only, and RHL is infinite value. Since RHL is infinite value, we can say that it is still infinite type discontinuity only. We say that f of x has what type of discontinuity? Infinite type discontinuity. Infinite type discontinuity at x is equal to 0. At x is equal to 0 because right hand limit is infinity. Okay, now so remember this. Next, we will go with the last type, which is it is not harmonic, it is oscillatory type discontinuity. Oscillatory type discontinuity means, dear students, in this case also limit does not exist. Limit does not exist. But for what reason means, the left hand limit will not be defined or the right hand limit will not be defined. For this reason, the limit will not be defined. Okay, now, and hence we say that the function is discontinuous. So let us take an example to understand what is an oscillatory type discontinuity. And one of the best examples is f of x is equal to sine of pi by x. But remember, x is not equal to 0. If you try to find left hand limit, what happens, dear students? Limit x approaches 0 minus f of x. That means sine of pi by x. So sine of pi divided by 0 minus, that means what? Pi divided by minus 0.00000 and so on. This value is approaching minus infinity, correct or not? And what is sine of minus infinity? Don't say minus infinity as or plus infinity. Sine of any value is always between minus 1 and plus 1. The answer is between minus 1 and plus 1. Okay, na? But the problem is that we do not know what is that value. It is a finite value. The answer is what? A finite value between minus 1 and plus 1. See, the left hand limit, okay, na, is a finite value which keeps oscillating between two outputs. What are the two outputs? Plus 1 and minus 1. It keeps oscillating between two outputs, plus 1 and minus 1. Okay, now so it is a finite value between minus 1 and plus 1, but we do not know what is that finite value. We cannot say what is that finite value. For this reason, the left hand limit does not exist, or left hand limit is not defined. We can say something like this. Similarly, what about right hand limit? Limit x approaches 0 plus sine of pi by x. Then it is nothing but pi divided by 0.000 and so on. Then pi divided by 0.00 and so on means what? Plus infinity. And sine of plus infinity is also a finite value between minus 1 and plus 1. But we do not know what is that finite value. So we can also say that the right hand limit also does not exist. Or right hand limit, let us say that right hand limit is not defined and left hand limit is not defined. Both of them are not defined in this case. Left hand limit is not defined and right hand limit is also not defined. Therefore, the limit does not exist. Limit does not exist. Okay, now you try to use any app, graph generating apps. Okay, now, and you try to see how the graph of sine pi by x looks like. Exactly when input is approaching 0, the output seriously toggles between plus 1 and minus 1. It doesn't take any fixed value. Yeah, don't think this is, sir, you can draw it continuously na. Why are you saying it is discontinuous? You might think like this, but it toggles in such a way that you cannot see any continuity between this point and this point. Okay, na? If you let me say like how will the graph will be means like this. It will be like this without any particular continuity. So okay, you can just check it once in any graph calculator app. Okay, so you can check what is the graph of sine pi by x, particularly when x is 0. Obviously you can see that graph, and obviously when x is equal to 0, sine of infinity, we do not know what is that value. So anyhow, the limit does not exist in this particular example, and we say that it is of what type? oscillatory type discontinuity. Okay, now if needed we'll see more examples of oscillatory type discontinuities when we discuss about discontinuities in problems. Okay, now so but the question is, we have discussed three types of discontinuities: finite type, infinite type and oscillatory type. But why all these three are called non-removable discontinuities? Because we cannot redefine the function, okay, to remove the discontinuity. It is not possible to remove the discontinuity in these kind of cases. It is not possible to redefine the function to remove the discontinuity. Okay, for that reason we say that these three discontinuities are called non-removable discontinuities. Okay, this is an important point to remember, dear students. Okay, now so what is it? We check continuity of a function only at the points in the domain of the function. Okay, now we discuss about continuity only at the inputs which are in the domain of the function. Keep this in mind. For example, okay, now what is it? I'll redefine. So what is it? We don't talk about continuity of f of x which is equal to tan x at x is equal to pi by 2. Why we will not talk about continuity of tan x at x is equal to pi by 2? Because x is equal to pi by 2 is not in the domain of tan x. Okay, so if you want to talk about continuity of the function tan x, you discuss about it only in its domain. What is its domain? All real numbers except odd multiples of pi by 2. So in this particular domain you discuss about continuity of tan x. If that is the case, we will say that tan x is continuous in its domain. We will talk about it in the next video. Okay, now continuity of a function in a given interval. But anyhow, what I am trying to say is that we discuss about continuity of a function only in its domain. Okay, now but we discuss about discontinuities even at points which are not in the domain of f of x. We discuss about discontinuities even at points which are not in the domain of f of x. Example, f of x is equal to tan x has a discontinuity at x is equal to pi by 2. You can check the left hand limit and right hand limit. Obviously they are not equal. It is infinite type discontinuity. See, once again I am saying, from this I can conclude that tan x is a continuous function, but at the same time it has discontinuities at x is equal to pi by 2. But tan x is continuous only in its domain. Tan x is a continuous function only its domain. So therefore the word continuity is used only for points in the domain of the function, whereas the word discontinuity can be used for all points, even the points which are not in the domain of the function. Even for the points which are not in the domain of the function, we can talk about discontinuities. So therefore tan x is a continuous function in its domain, but it has discontinuity at x is equal to pi by 2. Even it has discontinuity at x is equal to all odd multiples of pi by 2. You will get more clarity about this concept when we discuss the problems. Okay, so in the next video, let us discuss about the continuity of a function in a given domain. How can I say that a function is continuous in a domain? And we will also discuss about directional continuity, and after that we will solve the problems based on the discontinuities and also continuity in a given domain, and at the same time directional continuities. So that's it in this today's video, dear students. I hope you have understood the types of discontinuities very much clearly. So if you have understood it, do like the video and share it with your friends, and subscribe to the channel in case if you are new, and let me know if any feedback is there in the comment section. Thank you. See you all. This is Sandeep Kumar in the next video.